Good morning, everyone. Hi, guys.
Good morning, sir. This is Suresh.
Good. Good morning, Professor Suresh. How are you?
I'm doing good, sir. How about you, sir?
Very good. Thank you. So,
Sir, if you don't mind, your voice is not clear, sir.
just a second. There's some background noise.
Okay.
Is it better now?
Yes, sir.
Do you hear any background noise?
Some sort of disturbance, sir.
All right. Is it better now?
Yes, sir.
Okay. So I trust all of the students have done the completed the internal exams and done well.
Yes, students, have you completed?
Yes, sir. We have road breaks.
Excellent. So due to that, I have delayed publishing the project announcement, which otherwise was supposed to be announced last, or rather, Monday, the last Monday. So I chose, as you have seen the announcement this morning, I chose to announce the next project, which is based on linear regression, linear regression. Today, it started that project announcement by the overview session. So, did all of you have a chance to complete the last project, this year project? Anyone need any help? I did not check today or yesterday, but I think 3 days back I saw 70 submissions. I'm not sure if Professor Suresh had any chance to look at that. Submissions are all 100%. Do you have a chance, Professor Suresh?
Sir, I couldn't get you, sir. Could you please repeat, sir?
Did you have a chance to look at how many submissions are still pending or for the last project in the Google Classroom?
Sir, please, just give me a second, sir. I think there is some sound issue with my device. Just let me try to recorrect it. Just give me 2 minutes.
Sure. Students, are you able to hear me okay, or do you hear any noise from my side?
Sir, no issue.
Everyone- Okay. Thanks, Vishnu.
Sir, I guess it is from my end, sir, not from your end. Yeah, let me try to reconnect, sir.
Sure. Meanwhile, let me set up. Fill up the presentation. The session is already being recorded. So we're going to start. Okay, we'll wait for you, Professor. So please read them.
Sir, yes, sir. Sir, please tell me, sir.
Yeah, so I was saying, did you have a chance to look at the submissions of the last project? Is there any help needed to the students on the project? How many
No,
are yet to be submitted?
no, sir. Actually, like I didn't, like to be frank, I didn't see, sir, because we are having exam duties this week totally. And right now, even at 11 o'clock, even I'm supposed to attend my duty, actually, examination duty. Maybe after coming from that, I'll look it into it, sir.
No problem. Yes, yes. So I probably have to rejoin back, right? I don't see my third screen to share where my presentation is. Just give me a minute. I will come back. I hope you guys can hear me.
Yes, sir. Yes, sir.
Oh, I don't see screen number. Nice. Good to go. All right. So, do you see the screen share?
Yes, sir. Yes, sir.
Yes, sir. It's visible, sir.
All right. So, let's see. All right. Morning, everyone. So, we are delayed by 13 minutes. Apologies for that. So, today's topic. So, before we start today's topic, I just want to re-emphasize again that the the last week's or the last which is the principal component analysis. If anyone still has any questions to complete the project, please do get in touch with me, and I'd be happy to help you guys. So having said that, I also would like to know that you were able to do the internal exams very well. That being said, let's get back on the screen. We have break. Now let's get back to our stream of sessions. We have one 8 algorithms and we have completed one fundamental algorithm, which is not on the learning, but which is a tool for the machine learning analysis. Any questions in the last project or on the last topic, which is this, before we start talking about the first and the most fundamental algorithm of machine learning called machine linear regression. Any questions?
Sir, no questions.
That's it. I didn't get to that. agenda. Right, so today's algorithm topic, and for this week is going to be linear regression. Regression is essentially a statistical term. So I'd like to introduce what the heck is the linear regression and what's the mathematical model and how do essentially we understand the regression in the context of data sets, data population. Essentially, data set, data population are two terms.
Excuse me, sir. Excuse me, sir. Sorry to interrupt. It seems there is a slight disturbance from your end, sir. Just now I got message from students.
Yes, there is. There is a little work going on in my room. In our
Okay.
kitchen.
Understood, sir. Understood.
So that should be done probably in another 5-10 minutes.
Okay, sir. Fine, sir. Fine.
All right. All right. So, just a second. We can. All right. It should be minimal now, or probably zero. So how do we? How do we understand the regression in the context of data population data sets? Essentially, these are statistical terms. Probably the mother of all of these, the root cause for all these statistics, learning, and the models potentially could have come from, at least in a way, from the population census, which should have started hundreds of years back by the governments and essentially the local or the state. They wanted to get the data and then derive some hypothesis. How many people are there about, let's say, who's having a wealth of 1 crore, 10 crores, hundreds of years back, a few lakhs of people. So all these essentially originated in a way from there. Essentially, that study was called statistics. Take a sample, even for who wins the elections. We take a sample of top each 5-10 people in each town across 100 towns and see who's going to win, which party is going to win. It's based on take some samples and then based on some mathematical models arrive at the results for the entire set of population of constituents. So we're going to see how visually the regression is related to the data set. I wanted to get you an understanding of that. And then a mathematical model of linear regression. And the mathematical model of how do we train linear regression model, and then how do we compute mathematically the regression coefficients, also known as weights. Weights is a term. Probably we all know weight, when somebody says, my father owns 100,000 crores, you take that statement and the friend who's also the hostel here or the roommate says, my father has 1,000 crores. You immediately believe it, you say, I'll discount it by 50% or maybe 99%. That is the weight. The same way, models also use the weights, right? Which based on type of mathematical model you are using to learn. Either they're called weights, coefficients, or essentially, one of these two factors, weights or coefficients, etc., etc. And then we'll talk about the project. That would essentially a project where we can apply linear regression, which is again a fundamental block or fundamental project that across the globe, whether west or east, US or Europe or any other country, potentially US, they use this Boston housing data. I was trying to build a project based on our Ministry of Earth Sciences, Indian government to predict the temperature. Somehow that was not the right example. In fact, I spent around 2 days building the project to predict the temperature for next 1 year, monthly temperature based on the temperature that the government has published 2 years back, 1 year back, from 1901 till 2021. Each month, each season, and annual mean temperatures have been published by the Weather Center of Pune, which is essentially by the Department of Earth. But that did not go well. So I switched in the last minute to the Boston project, Boston housing project. Also, few parameters about how do we determine the efficiency of the model and the accuracy of its prediction, or also called inference. And then I will try to demo you guys. I put the code yesterday, so I hope it would work. Should work. But PDF generation, I have some issues in generating the PDF because I switched my laptop to a different laptop. It requires some latex dependency. So that's what we're going to be. I'm going to be, sharing the footage today. So, any questions on the agenda? And then obviously we'll have Q&A. All right. But without much ado, let's rock and roll. There are no questions. So, any prediction inference is you have some data already, also called historical data, about something. Be it winning the election, be it the past results of the elections, constituency-wise, or be it about, let's say, the biggest stock in India today or across the globe. NVIDIA, probably, I think, $3 trillion company. 2 years back, its price was around $100, or maybe $10, and now I don't know, thousands of dollars, and its value is it's grown from $100 billion company to $3 trillion company. So, how was its stock price in the past 2 years? Everyday stock price, historical data we got. So, essentially, when you want to make some prediction or inference, you have lots of data about a thing. It's historical data, which should have been not just in one angle, but it could be multiple angles. For example, you're trying to buy a plot near polarity number, right? 10 years back, if you tried or if you bought a plot near engineering college, or square foot would have been 1,000 rupees, or maybe it's sold in the square yard, must be around 9,000 rupees or 8,000. Now, today, it may be square foot could be probably 5,000. I don't know, but I'm sure it's gone sizably, multiple factor times up. But is it the same case for all plots? Not necessarily. If the plot was very next to polarity current, then probably value would have gone up more. And also its initial value 10 years back would have been more than the other. So there are various factors or angles or features or dependencies that when you're trying to predict or the value of what you're trying to infer or value of in scale plot depends. So this picture here essentially tries to show, imagine the value of the plot, thousands of plots next to the polarity nagar or engineering college, based on, let's say, X is its square footage. How much square foot is that? Is it 1,200, 30 by 40, 40 by 60, 50 by 80, or is it 300 yards, 500 yards, 600 yards? Imagine that is one variable, one dependency we are taking. That let's consider as X. And the price of that plot, Y, is a dependent variable because it depends on the area, at least in this case. So Y is shown on the Y-axis, X is shown on the X-axis. It's one variable, and in this case, the model is univariate model, or the prediction is essentially dependent on one variable, hence it's called univariate prediction or inference. And obviously, y is a function of x. And in this case, x is a single variable. But if the x, let's say, you have a data that was collected by somebody next to Polarity Nagar. I think there used to be some Don Bosco school. Probably some student came out and saw this. He wanted to build a business of real estate. And then he started collecting data. What were all the factors that people or the price was depending? Not only the area, but how far it is from the main, how far it is from the polarity card. And there must be lots of other factors that must have come up after I left. Only these are the two that are striking or vividly I still remember. Right? So he or she must have collected all those parameters, must have created essentially some sort of table. One column essentially is that value of that plot value. The other are various columns of how far is it, what is its square footage, and then whether it's east facing, north facing, these will have a higher value. Lots of factors. Is there any symmetry next to it? Then the value will be lower. All these factors have some influence, or the value of the site is dependent on all these factors, and each factor is also called the features. Each factor having some sort of weighting. Remember the discount factor I talked about when your friend said my father home has 1,000 crores of work, you discount it. So that since you're bringing it down, it's called discount, but essentially it's a weight, it's a factor, it's a weight. So the inference or the output is a function of other variables that are independent and they have some weight. So is it always so? Just to draw one line, one point here, you see that black line here is essentially that's the main area or the mean area where the data or the price seem to be concentrated and being trended. So, of course, there are the dots or the values that are lying around above and below, varying status. Essentially, it's called variance. It's hard to say the data. But the central line seems to be more closure where the data is trending towards concentrated as a line, or it is kind of a line that tells, if you know a value on X, you can essentially identify what's the value of Y based on this line, because the calculus and then essentially bring in multiply the slope of this curve and with some offset from the origin or the intercept on the y-axis or the offset from the origin at the bottom. You can essentially take the value of the x part, the y part. Will always the data be trending in the straight line? Necessarily. So if it trends in the straight line, it's linear. If the data is concentrated not necessarily as a straight line, but as a curve, which is not linear. Essentially, anything straightforward is called linear. So we use in our daily life. Anything that is not straightforward is nonlinear. It's a curve. It can be any curve, hyperbola, parabola, combination, multiple non-linear structures being joined. So essentially, your independent variable is shown on the x-axis. A dependent variable, single variable here in this case, because it's two-dimensional space. But with multi-dimensional space, we talked about polarity or the site next to the polarity cards, right? The site value we are predicting is scalar, one dimension scalar. But it could depend on multiple factors of acreage, footage, its direction, facing direction of the site, Those are all various angles, features, and hence it's a multivariate dependency, right? So to summarize, you show the independent variables on the x-axis. We showed when we distributed or visualized the data. And we have shown the dependent variable single. If it is, we are predicting only one value or a point, a value which is scalar. We can also predict a vector, but I think that's the most advanced. We would not be covering any topic here in this lab, but I'm sure that when you get your masters, you start looking at predicting a vector which has multi-dimensions. So you have the data, historical data that you plot them as data points, and they will have some pattern. Usually, if they have a linear trend or a pattern, like a line, that line could be in any direction, straight up, inclining down, horizontal to X, horizontal to Y, in any direction. Then a linear regression model, because it is like a straight line, and based on its slope, which is calculus, essentially gradient is, or essentially gradient is nothing but the slope, which is nothing but the first derivative. Using the linear regression model, you can potentially predict or infer the value, unknown value, unseen value, if you know the value of dependent variable. So that line is essentially called a line of regression. This is where the data is regressive, getting populated again and again. Regression also is a term used in software engineering to test various features of a product that were already delivered and deployed, but because of a new feature, whether the previous feature got disturbed, if any bug creeped into the feature. That type of testing also. Testing again and again. It's called regression. Essentially, it's a repetitive. Data is getting repetitively populated in some form of pattern. Right. So we understood the regression, we understood the data points, we understood the dependent, independent variables. Right. Now let's look at, try to put some 3-4 points around what is a linear regression in a more formal way. It is essentially a statistical method. What is statistical method, or what is statistics? Where there are numbers, you make some sense out of numbers is statistics. That sense is not for something that already you know, but for something that you do not know. You try to infer, you try to predict something that you do not know based on the data set or based on the statistics or stats in short that you already have. You try to infer. And that infer could be predicting a value, inference, or predicting a class, a category, like yes or no answers, like various type of categories, or it could be a continuous value, or it could be a probability, right? So statistics, it's a that is statistics, it's a statistical model in which the value that you're trying to predict is a function of other values or other independent variables or values or features, etc. And the value that you're predicting is essentially decided by those independent features. In polarity measures plot case, we have the value of the site is a dependent variable. The area of the plot is independent. The direction or the facing of the plot is independent. How far is this site from the main road which goes to Nandyal, right? Independent variable. So these are independent. They influence the value of the site. They influence, or they decide the value of the site. Collectively. There could be some some, brain variables that may not have any dependency or may not have any influence on the predicted or inferred value. And we have found a method, we discussed this method initially. How can we find those that can influence the variable or the dimension that can influence the prediction? Anybody remembers what is that method known as?
The correlation.
Principal component analysis. Which are all the principal components or principal dimension, principal feature, right? So from how many? 113 or 113 features or dimensions to be reduced to 55 features in our PCA project, right?
Yes, sir.
So essentially identifying which will influence, which features, which variables influence your prediction of unseen value, right? So, yes. We talked about the examples, predicting the stock prices, weather forecasting, housing prices, right? So you may ask a question, are all these linear? Particularly, do they follow any linear pattern there? Value of, let's say, stock. It may not be linear. For example, let's say Dhirubhai Ambani all of a sudden, not Dhirubhai, elder Ambani, Mukesh Ambani announces today, Geo Telecommunications has formed a partnership with, let's say, or buying AT&T in US. All of a sudden, its stock price, whichever X today, will get doubled to X. It's a huge market, dollar market, AT&T in US and that one. And the stock price jumps up day after tomorrow when the stock starts getting traded, maybe 2 times. It's not linear, right? It's not linear, but over the time, even those non-linearities can be approximated to be linear. If you take a 5 to 10 year period, one day short blip, which is 2x, over the 10 year period, it may look completely linear. It's something related to in probability and statistics. A similar philosophy called central limit theorem. Some of you guys might know it and may learn about the Gaussian distribution and normal distribution. Any data, any distribution, when you have sufficient enough, it tends to be, whether it's linear, non-linear, the data distribution tends to be a standard normal distribution. Essentially, there's a mean, and then mean is mu, and then its variance is sigma square, and it's a bell curve. Essentially, it becomes a bell curve. Right? Whose probability, the data distribution, probability distribution, entire area under the curve is 1, right? So that's about the linear regression. So we also talked about the single variable based univariate, multiple variable based, or multiple dependencies based, which is multivariate regression. Not necessary. It's a common sense that tells if you're trying to predict the price of the plot next to the college. It is common sense that the more factors that you consider, you may get a better refined prediction. When you're trying to buy, you also look at, is it next? How far is it from the road? Is it not facing? What's the area of the site, etc. But there is a limit beyond a certain number of variables or dependencies. Anything above that may not make any sense. So it is essentially there has to be a limit to the number of variables beyond which the prediction efficiency or accuracy may not have any significant input. That's it. So if you look at the data, so this is the project data, Boston housing data. Essentially, it's nothing but housing value, just like the site that I talked about. This is a house value in Boston, Massachusetts state in the US. The value, the median value of that house, which is based on various factors, whether this house is in the area where there is a huge crime rate, which colony or town this house is. So there are various around 13 to I think 13 such parameters. Whether is there any industry next to it? Is there any commercial building next to it? Usually Westerners prefer not to be in the commercial area, whereas most of us prefer to be in the near to the commercial areas in town. Whether there is any education institution that has a better pupil to teacher ratio, right? And are there any people or in bastis? Basti, right? Is there any area where there are a lot of low income or those people that have a temporary dwelling, bastis? So those columns that you see are nothing but the independent features or variables are also called in the context of regression, because your regression is nothing but a linear combination of these independent variables, are also called hence regressors. Right. Each column is a variable / dimension / regressor. What is the value that is dependent on all these columns or regressors or features is your predicted value or your response rate, or also called target rate. People call it the multitude, myriad of names, but all of them mean the same. Dependent variable, predicted variable, inferred variable. But in this case, it's a scalar, one variable, which is the value of the house, like a site of like next to it. Hence, the input in this case, if you are trying to predict, let's say, the value for this particular house entry at 0th index, which is the first entry, the value is 24. It's hundreds of thousands of dollars. So 2,400,000, 2.4 lakhs essentially. 24 into 100, 2,400, so 24 lakhs, which is 2.4 million. It's 24 lakhs of dollars. So this is your regressor or response variable, and the rest, all of these are your regressors. Regressors are crime, then zone, then next to industry, and there is a very popular Hudson River. Charles River. Hudson is the capital. Charles River is in the Boston. And somebody having a house facing the river is well maintained. Obviously, will have a better value, higher value. Unlike the houses in Kannur, which potentially are next to Tungabhadra River, may be laden with lots of dirt and dirty things that the people would have done on the shore of the Nile, of the Tungabhadra River, right? When the river is well maintained, and hopefully it will be Tungabhadra River in Kannur town, values of the houses will go up multiple times. So all of these factors can be represented as a vector. All of these values, 13 columns, can be represented as a vector. 13 columns and 13 elements or constituents of that vector. Hence, this vector is a 13-dimensional vector. These are the dimensions in which the value of the house is dependent or is decided by or is dependent upon. So when you have something, set of things that influence one outcome, those things that influence can be considered as a vector. It's a space with those many dimensions. It's not really like when you say a vector dimension beyond 3, which tensors and matrices that you try to get into, you try to derive some values and do the processing. Does not mean there is a real world with those dimensions. Probably we don't know. Maybe some of you might have seen the movie Interstellar. You'll probably, or many of the movies of this guy, Chris Nolan, what's his name? Inception movie director, where you can go beyond to try to see more than 3 dimensions, but humans can't see beyond 3 dimensions. And we probably can visualize mentally, but we cannot physically build it. But all these dimensions mean essentially each thing influencing the outcome. And you are mathematically building a multi-dimensional space of, its weight, its distance of that value from the outcome that we want to predict, which should follow a pattern and stick to the weights or the distances of the other factors or other dimensions as well, or other features. All right, so let's try to understand a little bit of or visualize mathematically the regression line and the data that you see. So you have seen this slide. Okay. So this is the line. How do you represent a line mathematically? If in a 2-dimensional space, let's say x in a 2-dimensional space, I have a line like this. What would be its a mathematical value, guys? Anyone can respond?
So y equals to mx plus c.
Excellent. So what is m there?
So slope, sir.
And how do you get a slope mathematically if you have the line with you, with the parameter?
Sir, either by using difference in y coordinates by difference in x coordinates, sir, or using derivative formulas, sir.
Absolutely. So derivative is nothing but what you said first. You said 2 things. The difference in dividing the difference of the coordinates, x, y coordinates, x coordinate, delta x by delta y, right? The difference is delta. So the difference, you take some reference and then you divide the difference of x with y. That's nothing but your derivative, right? And this derivative is being used across. It's pretty simple, but we tend to not to correlate from our childhood, high school days. We know all these simple basic mathematics, but it is used immensely across trading, predicting the stock price. Anyway, coming back, y equals to mx. M is the slope, x is your input value, whichever point you are picking. If you are picking a value here, so the x is this value. If we are picking, right now we have here, xi is the value, and the corresponding, we want to predict corresponding yi or y to that, and then you can, this is the slope beta 1, you'll have to derive, You can derive it based on the data that we have, right? The slope. And then what is C?
Sir, y-intercept, sir.
In this case, this is the beta 0. Right. And if it is X, if it is like this would be your intercept. The intercept or this offset from origin, essentially. Also called in machine learning terminology, what is it called? Anyone? Bias. So you are already started. Let's imagine. Can you tell me how much you like your friend on a scale of 1 to 10? You already have opinion about him. So you already know maybe he is 5. But let's say he's helped you in the last 2-3 days. Then if you already know I rate him 1 to 5 based on my past experience, but yesterday he has done something good for you, then you may take 1 or 2 notches up and say 6 or 7. But that 5 is you have built that bias over the last 1 year, 2 years, or however long you've been friends with him. So that is essentially the bias, right? And offset from 0 origin, right? So go back to the talking about things here. So I'm going to undo that. All right. So clear. Okay. Right. So this is the regression line. Okay. So this is the regression line. Xi dependent variable, we talked about it. Sorry, independent variable, dependent variable. And this is intercept. Let's say we'll take this point. We are trying to predict this point, or we predicted this point. So how can we express this point, or how can we express the y value of this point in these 2 coordinate systems? We have the formula here, right? Y is nothing but the intercept beta 0, which is your bias, which we have addressed here, and then mx, right? You mentioned mx. In this case, it's called beta 1 and xi of that x parameter, which is xi here, x value. So slope times the x plus we have predicted. We don't predict. We may not predict 100% more. Probably God can predict everything 100%. But our prediction is always little away from the reality, either this side or the other side, positive or negative. So that's some prediction error. So we can express a dependent value or the inference as a combination of some bias and some prediction error, and then the prediction of linearly populated data with a slope beta. Usually people combine the prediction error and then the intercept or the bias into single. So that's where y equals to mx is. Right? Or y equals to, in here, beta 0 plus beta 1x. Right? So in the Boston housing, let's talk about trying to build a mathematical model. We talked about y equals to beta 0 plus beta 1 x I. Right? If we go back to the Boston data set here, we have more than one independent variable, which are, we have 13 independent variables. Out of them, we will get 30, on which the price of the house depends. It's a median price, right? So the price, if you know these values, we want to predict the value of the house whose various 13 values, regression values are these. The crime rate surrounding that area, which zone it is, whether there is an industry near to it, how far is it? If it's near to Charles River, obviously 0 means it's not near to Charles River or it's not on the bank of Charles River. Is there any nitrogen oxide emanating nearby? Is there an industrial area, right? A little bit, some units here. So the value of this would be a linear combination. Linear combination is your regressor with some weight and sum of all such regressors with weightage. That is essentially your linear equation. So here, let's leave out this. This x1 is your, let's say, crime, x2 is your zone, x3 is, let's say, your Charles River, whether it's near Charles River, 13 is 13 parameter. And they are multiplied with some weightage, which are called regression coefficients or weights. All of them are added up, and then some bias or intercept. There may be an initial value, right? When you're trying to buy a value, buy a house. Nowhere in the world, house value would be zero. Anyway, right? Even if it is in the jungle, probably it will have maybe 1 rupee, 10 rupees, 100 rupees, $1. So there is always a minimum or a bias or an awesome. So that's that. If you consider that, if you consider that case, then you have some value which is your regression coefficient H0, and we are using 1 as a convenient because that regressor always has a value 1, which is called bias, and the bias value is this, which has a regression coefficient. Give me a second, let me find out how long this is going to work. A couple of minutes. You guys can manage with my loud voice, with background noise being killed. Is that fine?
Yes, sir. Yes, sir.
Okay. So we talked about here the bias. We talked about the regression coefficients. Obviously, the other one is not level, right? That prediction always has an error. How do you find this error? If you know, let's say, go back. So how do you find the error? Model error. Anyone? Let's take this case of 4th row. We know this 4th row, meaning we have the values of the regressors with independent variable, which is 0.06, blah, 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 blah. And we know the output or the predicted, we can use these 13 values and predict them. Now we know the actual value of this house that was sold it. How do we find the prediction error, guys?
So first we try to predict the outcome, sir, and then we try to subtract it from the true value, sir. Predicted true value minus predicted value.
So you predict or infer based on these regressors. You have built a model. You've also identified what are the weights. Weights remain constant, and the regressor values are changed here. Now you applied these values in your model, and you have computed y value, which is your predicted. Now take that value. That will definitely be not 100% as 36 point. So there would be some gap or some error, right? Some deviation. So you take a difference of this. It could be a minus or plus, but it's a divergence. So that is your model. And our goal is, can we reduce that to 0? So such that we can find coefficients which can give us for any data we take, seen or unseen, trained or not trained. If that error is 0, then it is a perfect model. And it's nearly impossible to get such model. It may be like 99.999% accurate for that. Right? So regressors, bias, regression coefficients, and the model. So simply the mathematical model. K is nothing but your index, which sample you are addressing. If you have 10,000 samples, if you are training, you take 99 samples. So that means y of 99 equals to H0, which is the coefficient, regression coefficient of the bias, 1. And then H1, regression coefficient of the first regressor. And the value of that regressor for that sample, which is 99th sample if you are trying to take it for that, or trying to train for that particular model for that particular row of 99 or sample. Blah, 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 H1, H2, and the model error. So it's nothing but a linear equation. The first order linear equation. There's no exponent for regressors are the way. All of them have the exponent one, first order, right? Easy. So if an equation where a particular variable similar to this has an exponent of 2 square, what do you call, what order such equations do you call them? Any guess? Second order. All right, so let's put a pure mathematical equation for that. So we'll see this equation, understood this equation. And this is where the trick is. And this trick is, the next trick is crucial. All of you should pay attention and understand. Because this is the fundamental computational philosophy or computation philosophy of any machine learning algorithm, be it linear, nonlinear, regression, deep learning, neural networks. This is the fundamental model. This is the model that each machine learning model uses for training. And it is driven by mathematics. So matrix is nothing but a mathematical convenience of organizing various dimensions or regressors as a dimensions, and also in a structured way, in a grid, and applying the known arithmetics, basic arithmetics, which is nothing but multiplication or summation, right? So if you take this equation, using my cursor and I have put an ellipse around it, you can express this mathematically using the matrix and vector computational convenience mathematics or calculus. Consider, now let's try to be a little creative here. These coefficients H0, H1, H2, which are the weights, consider them as a separate independent entity, as a vector. Vector is always has only one row or one column. Usually vector is represented as a column, but it's written in a row using the transpose. When you transpose a column vector, one column vector, it becomes a row vector. So it becomes, so I said x0, x1, so it's not correct. It's the regressors, x1, x2, x3, right? Yeah. So let's take x1, x2, x3 regressors. Let's put them as a vector, a row vector. Let's take the coefficients as a column vector. Right? If you see here, I'm taking x1, x2, x3 values for that particular row, fourth row or fourth house in our case. Whereas x0, h1, h2 up to hn. What would be the hn value? N value in here? Any guess, guys? How many coefficients are there? How many coefficients are there here in this equation?
So 14, sir.
Why 14?
Sir, it's not bias, sir. Other 13 are the coefficients of 13 regressors, sir.
So key point that all of you should remember. Regressors are always, or the regression coefficients are always +1 of the dimensions of the input vector. If your input is 25 dimensions, your regression vector would be 26 dimensions, n+1. That 1 is for the bias. Right. So when you multiply a row vector with a column vector, how would the math work out? So anyone can I'm assuming all of you guys know how to multiply the row vector with a column vector. We have in this row vector, we have regressors, but we have regressors, 13 regressors. And in this case is 13. All these 13 regressors correspond to the fourth row of the table for the fourth house. But we have in the column 16 or 14 elements in the column. We need to have the 14 elements in the row as well. That is where you can see the convenience we have used 1, which is one value as the first element in this row, which will now help us to conveniently structure them as vectors to do a matrix multiplication. So this is it. Can somebody tell me now what is the size? How do you represent the size of this vector, regressor vector? What is the size of x bar transpose here, guys?
So 14.
No, how do you represent as a matrix? This is a matrix multiplication, right? So n cross m matrix means what is n? What is m?
So rows and columns.
Correct. But what is n? What is m? Which is rows? Which is columns? When we
So
say
n
matrix of n by m.
Sir, n is rows and m is columns.
Correct. Now, how do you represent this vector as a matrix now? Can you tell me its size as n by m?
So 1 cross 14.
1 row and 14 columns. And the size of this coefficient vector, column vector, what's its size as n by m?
14 cross 1.
Absolutely. And the error also, there are 14, right? So 14 by 1, because you are going to sum them up. So you can only sum the same dimensional either column or row vector, correct? So we can represent this row vector as a transpose of a column vector, which means x bar is a column vector. 1, x1, x2 as a column. So it can be represented as x bar t transpose, H bar and epsilon. So we can say for any house in the 30,000 sample, K being its index, the price of that house, 10th house, 8th house is transpose of its regressors or its features vector multiplied with the weights that we would have arrived at by deriving based on some mathematics and some error or bias. It's a combined effect. This is the linear regression mathematical form. Any questions, guys? So this is the representation. For the entire training, so we have, let's say, 30,000 samples of training. M is 30,000. So we are talking about 30,000 rows being multiplied with, H bar, which is, we'll have that many number of columns. Right? And that is where so many millions of multiplications and summing. That is where the compute power today, world talks about you need a lot of computational power. It took 10 days to train 100 million how many billion parameters I talked about GPT-3? 75 billion parameters, right, being multiplied. Here itself, you can say it is 30,000 rows, and if you have 13 columns, so we are talking about 30,000 multiplied by 13 columns. How many is it? It's 4 lakhs. 4 lakhs of computations or multiplications and summing. That takes a lot of time, in some seconds. But if you're talking about billions of such computations, when you have, let's say, 20 million rows or data, it's going to take a lot of time. That is where the training time runs from minutes to hours to days to weeks. And that means a lot of compute as well. If you have one computer that performs this, it may take years. But then that's where you need clusters to divide and count. That is essentially where people talk about huge compute and huge time, huge data for training. Any questions, guys? All right, let's quickly go through. So I'm going to spend next 5 minutes trying to build a little bit of intuition about how the coefficients are expressed as a mathematical equation in the linear regression, right? Building on the concepts of mathematics, particularly matrix algebra that we just talked about, and introducing you to a universal fundamental block notion of minimization, essentially error minimization, right? So we saw why we just saw, right, this equation. Remember this? If you're building a career in AI and ML, or for that matter, as an engineer, this equation has to be part of your brain, part of your DNA. Anything in a linear world, in any linear world, be it psychological, be it mathematical, if you have lots of historical data about something, you can predict future based on historical data and multiplying that with some weights, some discount. My father owns 1,000 crores. Discount if it's 9%. So some weight and some error. You can predict anything if you have sizable data. Probably it's like what Archimedes said, right? If you can give me, what did Archimedes say? If you give me the center, what was that? Center of the earth, I can lift it, right? The same way, if you give me enough data about anything, I can predict the future. Probably you can say that, right? But it's not always easy to get lots of real data. You can get some junk data. All the data on the internet, and that's why people are afraid of, the hallucinations with GPTs, or because there are people who have expressed wrong things, wrong notions on the internet, and your training has been based on that mix of right and wrong notions, just like what people are claiming today. Tirupati Laddu has been adulterated with ghee, right? So you would get obviously some such adulterated outcomes as well. Right? So this equation is very, very critical. And this has to be there in your life as an engineer, particularly as an AI engineer. Right? Very, very good. So your output is a linear combination of all various regressors with some weight multiplied, the sum, and some error or bias or combination of both. Which means if you have to correct yourself, if you're training, you take the data where you know the output, the value, and the input, which is your regressors. So you predict independently y, right? Here. And then you take the real value. It should have been actually y hat. Any variable with a hat is a predicted value. There is a mathematical universal notation. If you are predicting something, y, and the actual value is y or y bar if it is a vector, y is a scalar, bar is always for the vector, and hat is always for a prediction on the top. Caret on the top is called hat. So y hat is x matrix. Capital variables, capital letters always indicate matrix. Small letters with a bar is vector, right? So you deduct, just now we talked about, you take the difference of the real, what you have predicted, and the real value. And that is your error. Your goal in the training is always to minimize this error. And how did you derive the error? Your predicted value, actually it should have been y hat minus y bar. And y bar is nothing but x. Here we are taking, in this case, we are taking the simple linear combination. So minimize that error. And in statistics, since error has some value, it can be a fraction, it can be an integer, it can be a big number, it can be a small number, but even a smaller number, we want to make it as small as possible. Limit, we want the error limit tends towards 0, right? Hence, we want to see things, even if it is 0.009 error, we want to see it in a magnifying glass, right? So that we will bring down that even 0.009 to 0.000009. Hence, we always try to take a square of that and take a mod of it, because this error could be positive or negative. You could have predicted higher value than the actual value or lower value than the actual value, positive or negative. So you take a mod if it is a scalar. If it is not a scalar, you take a norm. Norm of a vector is nothing but square root of square of each component, right? So you try to minimize that error. Error is a vector, as we have seen, right? It's not a matrix. Error is a vector. So vector, essentially the vector absolute value is nothing but vector's norm. Vector's norm is nothing but square root of square of each element. And then you square it. Essentially, you get the norm without the square root, and you try to minimize, which is nothing but this is the equation. This is the mathematical. And then you use the minimization, optimization techniques to solve this problem, where x is a matrix, h is a coefficient, h we have seen, right? It's a matrix of training times multiplied by the number of dimensions plus 1, the size of this matrix. So if you use one technique is the least squares problem. This is called, since you are taking a square, and the solution for this is, which is solved using matrix algebra. The H is essentially X transpose X inverse multiplied by X transpose times Y bar, which is your Y bar is your known values, labels, the known output in the training set. X transpose X, this particular value is called pseudo inverse of X matrix. X matrix is your data matrix, your data, entire data set with the dimensions of your regressive value. So obviously, just as a trivia, if you multiply X with its inverse, you should get the I. What is I? Anyone?
Identity matrix.
What is I matrix?
Identity.
Identity. So identity matrix will have what values and where?
So diagonal elements are 1, sir, rest 0.
Okay. That's this. So why do we use squares? I just talked about one point. We try to magnify it. So we square it. If it is 2, you square it. 2 square is 4. So that becomes bigger. Also, statistically, square of anything essentially reflects some sort of variance. Right? And also, you are looking in the magnifying glass, so you want to penalize any even a smaller variation or error. And also, when you square, this plus minus will become positive. If you know this side or that side, the difference. And then also squaring, and this is one mathematical theory, but it's very good, right? Squaring of any variable makes it smooth for differentiability, which is used for your gradient descent. If it is a nonlinear thing, right? Nonlinear equation, then we use the gradient descent to arrive at the minimum value. So anyone remembers, if you have an equation, mathematical equation with variables, which is smooth, which is probably a square function, how do you derive the minimum value of that variable? If it is a univariate, if it is multivariate, then it becomes a gradient descent, and then Hermitian metrics and all that kind of picture. But let's restrict it to only univariate. If you have a univariate second order function, how do you derive, or how do you mathematically derive the value, minimum value of that variable? Anyone knows? Remembers? I think it is told in the maxima, minima in your intermediate, and probably in 10th these days, but I believe I studied in 4th class. So you take the first derivative of that equation and equate it to 0, and then solve for that value. Then you get either maxima or minima, depending upon if your second derivative is negative. I think it's minima. If the second derivative is positive, then the value that you solve becomes a maximum. Right, guys? So it becomes easier. And this gradient descent is essentially was the till around last year, till around last decade was the go-to option to arrive at your coefficients by using gradient descent. Right. And also the closed form solution we just have. This is derived based on the closed form solution, this H1. Right. That's 5 more minutes. Let's try to spend the next 5 to 10 minutes on the project overview, and then we will do a Q&A. So, kind of talked about it. Boston housing, it's a data that I think is collected and published by American Census Department in 1970s or 80s. It has around 506 samples. 13 regressors or 13 columns. And all of those columns have been talking about it. So I've also announced, I'm sure most of you would have seen, what is expected and what are the implementation steps. So I mean, today, if you are an AI engineer, if you are into data science or if you are into machine learning, particularly a data scientist, before trying to build a model and predict the value or build a model with the help of the AAM engineer, he would or she would try to explore the data. That is called exploratory data analysis. What does a person explore when you have 30,000 samples, 300 samples about housing values, stock prices, or how did your product perform in the last 1 month across various states when you're selling it online, when you're selling it in the shop? Essentially, you try to see what is the average value, what is the variance, what's the frequency of each item sold, histograms, etc. Right? And how many of these features, what are all the relationships between these features? What is the correlation between each features, say? So that is the EDA. That is essentially ask you guys to build to try out. These are all available as just one-line code from the circuit library. And also build a model, linear regression for the median value, and plot the actual versus predicted value as a graph, smooth curve, and try to evaluate the model efficiency using 4 or 5 parameters. I spent a couple of minutes what these parameters. And then print the final regression coefficients or weights, and they will remain the same for this housing problem. If you don't enhance the model with more data when you get, in case if you get more, but otherwise they remain there. It's like your essentially your mathematical coefficients, your formula coefficient, right? Only the regressor values to generate the data. Any questions on the project implementation steps and project objectives, guys? Questions? You guys can hear me, right?
Yes, sir. Yes, sir.
Okay, let's move to the next. Yeah, so a couple of minutes just to give you a sense of what are these metrics to evaluate the linear regression model accuracy. So we talked about, I mentioned about 5 parameters. R square score. Anyone can guess what R is? It's related to an English word that you are already familiar. Correlation. It's the square of the correlation square. Square of the correlation score. Then the mean square error, root mean square error, mean absolute error, and mean absolute percentage error. So let's talk about R square. R square score, also called coefficient of determinacy. It is nothing but the correlation of the data that measures the proportionate variance. Like any square is measuring the variance in statistics, particularly when you're talking in the context of data sets, right? And it measures the proportion of variance in the dependent variable, which is your predicted outcome, from the independent variable, which is essentially your actual value here, the square of square of difference of actual value and predicted mean value. Bar is mean, right? That is dividing with your difference, square of difference of actual value with your predicted value, hat. Y hat is predicted value, yi is your actual value for the item. The difference is squared and summed across all observations, essentially during the trend. You deduct that this has to be one first, right? Your prediction and your mean value difference summed and squared should be same as your predicted value, difference of your predicted value with the actual value squared and so on. So if R2 square is 0, which means there is no prediction up, or obviously the model is not good. It's building on wrong regressions. But if it is 1, 1 minus 1 is 0, so this will not valid. But if it is not 1, then there is a variance, which means you can predict, which means there is a nonlinearity, which means you can build some sort of model. So that's R2, or rather R square. Then the mean square error, it's a mean. Mean is nothing but average. So number of, if you have n samples, divide the sum by n. So you are dividing something, squared error, sum of squared error with n samples. So that is 1 by n. We are summing up. So you are dividing it. So it's a mean or average. You are summing up across all samples. That is n. And what are you summing? You are summing the error which is squared. What is the error? Your predicted error, which is, you can do either y hat minus y or y minus y hat, doesn't matter, because it's a difference which you are squaring, eventually it becomes positive. Whether it's a minus or a positive, the difference when it's squared, it becomes positive. Right? So the difference of your prediction error squared, summed, and divided by the total values in the data set. Mean squared error. This is the error, this is squared, and this is the mean. Root mean square error, simply take a root of the mean square error. Mean absolute error. So what is absolute error? So this is our actual value. This is our predicted value for ith house. The difference between these two is the absolute error. Sorry, error. When you take a mod, meaning if it is negative, you make it positive. If it is positive, don't do it. That's the absolute or mod. So this is the absolute value of the error of the ith training. You sum it across all training samples and you divide by the total sample size or training size. That's a mean absolute error. Then mean absolute percentage error. It's pretty much related to math, MAE. So let's look at it. Mean absolute percentage error. So this is your absolute error. Since it is a percentage, you divide that by your actual value, multiply by 100, and since absolute, take a mod and sum all of them across your training and divide by n. So that's the mean absolute percentage. Any questions, guys, before we get into demo? So probably we'll wrap it up in another 5 to 10 minutes. Is that fine, guys?
Yes, sir. Yes, sir.
Let me share the screen. Let me actually do it. I guess all of you can see the screen. Yes, do you see the screen with the visual code?
Yes, sir. Yes, sir.
Looking to go. If I can run. If there are issues, we'll go with what's other thing. Something is happening. So so did you guys feel the Visual Studio, particularly code, particularly in context of machine learning and digital is something that we started seeing convenience and feeling seems to be pretty good. I know some of you have been using the whole app. I guess most of you have become familiar with the Visual Studio Code. Yeah? Alright. I'm not going to run the next cells because it's taking a long time. Due to most of the CPU time is CPU dedicated to a problem itself. Essentially, this is kind of some exploratory data analysis and to print some, not some, all the column names, and then the first head 5 values or 5 values of the table, load it, the data, right? Next is the EDA, where I'm printing the histograms with one method. Histogram is nothing but each parameter by parameter, and that parameter, what is the frequency of the values for that parameter? For example, 10 value between 0 to 3 or 4 seem to be quite high. So that means it's concentrated towards something maybe around 400 value per the criminal value or crime rate. Next one is the zone. Most of the data has in the zone 0, and that zone 0 has around 350 entries or 400 entries. Industry related, so pretty much the value maybe distance from industry between 17 to 19 kilometers away from industry is where a lot of data, a lot of people say preferring because a lot of data is having such a higher, more data with higher distance. So histograms tells you some insights, visual. This is what people used to use in statistics in the past. Now we have essentially mathematical models to perform. So this is the essentially the list of all the histograms or plots. Next is some correlation, heat maps across. Correlation is always between two variables, right? So you can see last slide one of you just mentioned also you can see this diagram. So correlation of crime with crime will always be 1, right? So negative indicates they are going in the, they have inverse proportion, inverse relationship. Positive value indicates they are related in the same direction, right? The value of any correlation lies between -1 and 1. Is that clear? Next stage, train and build a model. So it's built. Next stage, essentially 0 to 20% is what we take as a test, and then you can see green is the actual value and the predicted value for the 20% of 307 on each sample. 10% of 300 is what? 60 samples also. Then evaluation, evaluating the model performance, we go for the R2 squared is not such a big model, meaning it's not such a performant model. Any reason why? Why is it not 0? I mean, why is it not 1? We want 1, right? So that means that it's 40%. What's the MSE? We have 24%. Right? Mean square error. Any guess why it is not 0% NSC or 1% NSC, or accuracy is not 99%? Any guesses, guys? Data is less, training data. If the training data, had the training data been more, thousands of rows, then your equation, your equation and your coefficients equation would have been smooth, because the distance between the points is shorter when you have more data. Then your curve is smoother. Then your gradient, your coefficients finding is more accurate. But if the distance between the points is longer, then there is an approximation. So you would take a straight line. But maybe in reality, it may be a curve. It goes this way and comes back. So that's why the more the data, the more smoother curve, the more smoother gradient, or more smoother, better optimization that you can arrive at in minimizing the error, and the better values for the coefficients to give you the better accuracy of it. That's the reason always you need lots of training data. And then what are the final values of the coefficients that you have? And then of course you generate the field. So let's go back and see so Q&A. Any questions, ladies and gentlemen?
Some more questions, sir.
Okay. So was it helpful? You were able to follow?
Yes, sir. Yes, sir.
All right. So in case if you guys are interested in doing any Gen AI project or prototype, write to me at this email address. I'm trying to build some POCs from Brilliant on the Gen AI front using LLMs, and also DAG and RLGs as well. Anything you'd like to add, Professor Suresh, if you're there? All right. Maybe
So I think SAR is an examination duty, sir.
right. Any more questions, guys? Or rather, anyone? Any question? I see today not more people. So I hope I did not complicate the concept. I hope I have explained it in a way that you are able to get the fundamentals. I always try to give the practical example. So anyone remembers what's the next week's topic?
So I think multiple regression.
No. We have predicted a continuous value, right? Using linear. So linear equation, line, and predict a continuous value. What could be the next logical step in prediction in real life?
So
Something
logistic regression.
something that is not continuous but discrete. How do we predict our category? So is Mr. Chandrababu Naidu going to form the next government after 4 years? Or is he going to, his party is going to win the next, I don't know, surprise election? So some sort of category. Here in this case, it's yes or no, two categories, binary. But there are other practical cases where you would have multiple such discrete values of category or category. In which case, you need some sort of mathematical formulation that is not linear, because it's not linear. It's not a line. It's either this or that. It's non-linear. And for such categorical values, which is essentially a fundamental expression of mathematical expression for such non-linearities or categorical values is some sort of sigmoid function, also called activation function in neural network, right? It's an S curve. All these you must have studied in your signal processing, if you have signal processing, the 10 to 15 curves, and direct delta, the impulse. Many of you, if you have studied or taken some communications, you know the impulse curve, the delta, which is represented by delta, right? S curve, and then there is a value, release, rectified linear. All these bring in non-linearity, which is between 0 and 1, nothing but the probability. Also called, they are called sigma functions, sigmoid functions. Right, so that is the next topic. But anyway, this week's project, which is linear regression, I have extended the submission date till, I think, next Wednesday or Thursday. I hope all of you have seen the announcement. And the next project, which is the logistic regression, I'll try to announce it on Monday by evening. And you have time to submit till next Sunday. So with that, I would like to close this session. Thank you very much. Wish you all the very best if you are still writing the exam. Have a nice evening.
Thank you, sir.